HTTP2 HPACK. What is HPACK? HPACK is the protocol and algorithm used for header compression in HTTP2. It's a separate proposal from the HTTP2 standard and it's not an acronym. The specification is intended to be simple and inflexible. The algorithm is based on lookup tables and Huffman coding, and not on loopback-based compression like Deflate. If you're not familiar with Huffman coding, I added some simple Q&A on the right-hand side if you want to pause the video, along with the diagram over here with the sample Huffman code. So components of HPACK includes the basis of a static and dynamic table used to decode requests. This table stores the header and optionally a value that is defaulted for that specific entry. The static table is defined by the standard, while the dynamic table is constructed throughout the lifecycle of the TCP connection. So this would make HTTP a stateful protocol, and both the server and the client will be keeping track of these tables. Here's an example of a static table from the standard. We have 61 entries with header names and optional header values. For the dynamic table, it's a continuation of the static table which starts at index 62. It's bounded in size by a value set in the settings frame, or a default value of 4096 octets. Once the maximum is reached, the oldest entry is evicted. So this algorithm is based on incremental. So if we start off with the static table and then we get a request with two headers, header 1 and 2. At first, header 1 will be added onto index 62, but once you read header 2, header 1 will be incremented by 1, moves to index 63, and then 62 will be header 2. So since TCP has guaranteed order of delivery, the order will be preserved across the client and the server. So how do we reference the headers? We have four types of HPACK headers, including literal header field representation, header field with incremental indexing, without indexing, and never indexed. The first one is literal field representation. This one is used when both the header and the value are in the table, either static or dynamic. So for this, we have something like this. We have 1 byte over here, with the first bit being 1, the most significant bit. So if we want to do a get method, then what we do is we do 1, 0, 0, 0, 0, 0, 1, 0. So the very first bit is a literal field representation. So we have the 1, denotes that. And then we have the index number, which is 2 in binary. So we know what to do a static table lookup. We look into our table from before and we see we have a method get. And we're done. It's amazing. So with incremental indexing, that's our second type. For this one, we use it when the header value isn't available in the table, but we should be adding it. So this one has a code of 0, 1, the last one had a code of 1. So there's different cases to consider if the header name is already in the lookup table. So in this case, we have 0, 1 as the most significant bits, followed by the index. Afterwards, we're going to be adding the header. So the H represents if we're going to Huffman encode or not the string value. If we Huffman encode it, we set H bit to be 1. If not, we set it to 0, and then we simply send the raw bytes over. We first have to indicate the length, and then for length octets, we have the value string, which is padded by 1s at the very right of it. Meanwhile, if the header name doesn't exist, then for the index, we set it as 0, and then afterwards for the name length, we simply perform the same operation with the Huffman bit, and then the name string, which is the length in octets. So without indexing, so for the last one we got a header and then we'd index it. This one is for types of items that are likely to change in each request. For example, the path of a request is likely to change. For this one we have a code of 0, 0, 0, 0. These are the most significant bits, and then we have the exact same pattern as before. The Huffman bit, value length if the header already name exists, and if not, then we simply have the string here for the value string. So literal field representation never indexed, which is the fourth type. This one is interesting because it sounds very similar to the last one. We don't index or we never index. Differences for this one, even for intermediaries, such as if this is a proxy, we never index this into our tables. This is used for confidential headers such as passwords. So the format is used exactly the same as the previous representation, except with the bit pattern 0001. Okay. And then we also have something like this in the case where we have a header that's not already in the table. We need to supplement the name as well. So how do we actually Huffman encode? So the HPACK standard actually denotes a series of Huffman encoded values. So they developed this through a series of empirical tests with a lot of data. So this is a table from the actual specification. We simply map different symbols over to different Huffman codes. And we perform this process iteratively. Hope this video made sense and you enjoyed it, and there's a longer video in the description below with more details and examples. Thanks for watching.